This section is on sound waves, section 14.2. And so we're going to go into some detail here with sound. And we're going to break this up into several different areas. First of all, we can discuss what is our objective. What can we physically measure with respect to sound waves? And that's objectively measure. That's by physics. And then what can we subjectively measure? So we have objectively and subjectively. Objectively is what we measure in physics, like pressure, and force, and volume. Subjectively is what something seems to be to the subject, to the person. How loud, how soft, how consonant, how dissonant. So, what are these different things? First of all, we have the concept of the intensity. The intensity of the wave is how intense it is. It would be measured in watts per square meter. It is the power that is spread over a given area. So this intensity is measured in watts, which is power per square meter. But if we look at it subjectively, that loudness is how loud it seems to our ears. So this would be called loudness. So it's loudness to our ears, but it's intensity to a physical measuring device. Well, let's talk about loudness and how we measure it. We measure this intensity or loudness in terms of what is called decibels. And a decibel is defined as, we often use the symbol beta for decibel. I should use a capital B there, decibel. Beta, the decibel or loudness of a sound wave, is 10 times the log, it's base 10, of the intensity of the sound. The intensity is the watts per square meter, divided by the intensity at threshold. In other words, this is the softest sound that you can possibly hear. Now you'll notice that we've taken a logarithm of a ratio. This ratio has no units. And I remind you again that every transcendental function, sine, cosine, tangent, cotangent, hyperbolic cotangent, logarithm, exponential, all of these functions must have arguments. They must act upon quantities that have no units, that are dimensionless. And usually that is because they are ratios. Now, in order to compute this, we have to know what I naught is. But I is measured, box around this. It's going to give units of decibels. I is going to be measured in watts per square meter. That's our intensity. Well, what is this I naught? I naught is a very important quantity. It's the softest sound that can be heard. What wattage is that per square meters? The answer is 10 to the minus 12 watts per square meter. And so you have to know this, because it's the foundation of how we measure decibels. If we increase by 10 decibels, it's going to be perceived as twice the loudness. See if you can derive that. Well, let's look at an actual calculation. Let's imagine that we have different kinds of intensities. And as our first case, let's take an intensity equal to our threshold intensity. So we hear a sound that's the softest sound that can be heard. How many decibels does it have? The answer is beta in decibels is going to be equal to 10 times the log of I naught divided by I naught. We don't even have to put the number in. I naught over I naught, that's the intensity that we hear over the threshold intensity is equal to 1, but the log of 1 is 0, so 10 times 0 is 0, so the answer is 0. Decibels is 0 for I is equal to I naught. Now let's pick another one. Let's take beta for something like 10 to the 5th. I is equal to 10 to the 5th, 10 to the minus 5th watts per square meter. Well, if our scientific measurement measures this, what is it going to seem like to our ear in terms of loudness for that intensity? Well, we would have beta is equal to 10 times the log of I, which is going to be 10 to the minus 5th, divided by 10 to the minus 12th. And 10 to the minus 5th over 10 to the minus 12th, when we divide by this, it becomes 10 to the plus 12. So it's minus 5 plus 12, or 12 minus 5, which is going to be 7. So this is equal to 10 times the log of 10 to the 7th. But the log of 10 to the 7th is 7, and 7 times 10 is 70. So here we find that we get 70 decibels if we have this intensity. Now let's go to the extreme. Let's look at an intensity of 1 watt per square meter. What would that be? Well, that would give us a loudness of beta, which is 10 times the log of 1 over 10 to the minus 12, which is 10 times the log of 10 to the 12th. Well, the log base 10 of 10 to the 12th is 12, and times 10, it gives us 120. It turns out that 120 decibels is a painful sound. This is extremely loud rock music standing right next to the speakers or being on the tarmac when a jet is taking off. It's painful and to our ears, and it causes hearing loss and damage. So this is really our range. Our range is going to go from a decibels of 0 to decibels of 120. And the critical thing to remember here is that loudness, as it's perceived subjectively, is a logarithm of the physical loudness or intensity in terms of watts per square meter as a ratio to the fundamental watts per square meter. That's the threshold of human hearing. Okay, well, this gives us some idea of 3 different problems we've worked on decibels. Let's look now at frequency. Again, we have the what we call the objective and the subjective. Frequency is the objective, that is how many oscillations per second is measured in hertz, but the subjective is what is called pitch. We'd say he's off pitch. We wouldn't say he's off frequency. It is the pitch that gives us our perception of what the frequency is. Now, the musical frequency, pardon me, musical frequency is standardized now where the A above the middle C is 440 hertz. And this is the standard of all Western music. So a frequency of 440 hertz is the frequency that's a musical standard. Musical standard. And you must remember that. Now you can say, well, I don't know much about the piano. Well, let's imagine, for example, a piano momentarily. And this is going to be C. Remember, we have white notes and we have black notes. And it's going to be C, D, E, F, G, and then it goes again A, B, C. There's no sharp here. This has it. F sharp, G sharp, A sharp, then B does not have it. This is what's called a whole step, and this to here is called a half a step. This is called an octave from C up to the next C. And if we go to the middle C on a piano, is recognized by this pattern, and then go to this next A, this is called A above middle C. This is also called A440. So this A, right above our middle C, is our standard for music. And we're going to see later why that is so very important. The standard for acoustics is 1,000 hertz, or 1 kilohertz. That's the frequency for acoustics standard. This you must also know. So, for example, if you're doing hearing analysis, like do you have hearing loss and so forth like that, it'll always be referenced to the frequency of 1,000. It's kind of like in the middle of our hearing, a little bit more than this, slightly up above the middle A, but it's taken as the standard for hearing. Now, the normal maximum range, the range of hearing, we talked about the range of intensities from 0 to about 120 decibels in loudness. The range of frequencies goes from, for human, the range of frequencies for a human goes from 20 hertz, 20 oscillations per second, up to 20 kilohertz, 20,000 oscillations per second. That's your lowest note that you can hear. This is the highest. Well, what if a note is lower than this? A note that's lower than this can be felt as vibrations, but not heard as a sound. So you can sense it. So for example, if you have really good bass speakers and they're producing sounds below 20 hertz, you'll feel them in your body. You'll feel those vibrations, but your eardrums will not convey that to your brain. If you have higher frequencies than this, you simply won't hear them. In fact, most people, by the time they're in college, have already had some hearing loss, which we have all of our life, at the higher frequencies. And so many college students may not hear over about 10,000 hertz. The younger you are, the more you can hear those very high frequencies. So that's our normal range. If you think about what other animals can hear, a bat, it turns out, which you would probably think hears the highest frequency, uses echolocation. And indeed, they can hear 120,000 hertz. It's an interesting question to ask what animal or what thing can hear the highest frequencies. And so I'll leave that as an exercise to you. Let's next cover the concept of velocity of sound. The velocity of sound, referred to right here, I have to have my paper load just for a second so you can see what I'm referring to, is 331 meters per second at 0 degrees Celsius. I've written it right here. I have to move my paper. 331 meters per second. This is at our standard temperature. Standard temperature, the speed of sound is 331. But it turns out that it increases by 0.6 meters per second for each degree Celsius. So let's work a problem on this and see if we can figure out, at a normal temperature, say of 20 degrees Celsius, what would be the speed of, or the velocity of sound, or the speed of sound. So to do that, we're above this temperature, so we have 0.6 times 20, 6 and 6 is 12. Decimal point removes this. We're going to add that to 331, so we would have 343 meters per second. This is the velocity of sound at temperature of 20 degrees Celsius. So the velocity of sound changes. You must know this formula. You must know this value right here. You must know how the value changes. And you must realize that as it gets warmer, the velocity of sound increases. So we've talked about the velocity of sound. Well, what is the velocity of light? The velocity of light is 3 times 10 to the 8th meters per second. Something we've already discussed. Or 100, that's meters per second, or 186,000 miles per second. And that's in a vacuum. But in other substances, it's going to be different. Just like the velocity of sound is different in other substances. I want to mention here, though, that the velocity of sound in feet per second is about 1,100 feet per second. So this velocity of sound is 1,100 feet per second at our normal temperature range. And I'm not going to give you the connection, the exact values there. Just remember this is approximately true. And you also may remember a very interesting fact that we pointed out in one of the first few lectures was that cities in the United States were laid out to have about 10 blocks per mile. A mile is 5,280 feet. Therefore, it follows that one block is 5,280 feet divided by 10 blocks, so it's 528 feet. So 2 blocks would be 16, 2 and 2, 4, it's 5, 10. You'll notice that 2 blocks, 2 city blocks, is about how far sound will travel. Let me move that up, sorry. If 1 block is 5,280, we cross out the 0 divided by 10 blocks, 2 blocks is going to be about 1056. That means sound is going to go 2 blocks in 1 second. So if you see the lightning and then hear the thunder, then all you have to do is count it. And if you get, say, 3 seconds, then it would be 3 times 2 blocks or 6 blocks. That's very often a test question. It requires that you remember that 1 block is 1/10 of a mile, and therefore also that you remember that sound moves at about 1,100 feet per second, which is about 2 blocks in 1 second. Now there's another, this is a continuation of section 14.2 that I should write down here. Let me get a new piece of paper to mention that we've talked about the velocity of sound and the velocity of light. We can also talk about the velocity of a wave on a string. And it turns out that the velocity of a wave on a string, this is 14.2c, string, like a piano string or a tightly stretched rope, is going to be equal to the square root of the force divided by the mass per unit length. So as I put more and more mass per length, I'm going to lower the frequency. If I have very small mass per unit length, then I'm going to have a higher velocity. I should have said velocity then. If I have a higher force, then I have a higher velocity. And these, it turns out, will, because of that higher velocity, will give us a higher frequency. And as you know, the small piano strings give a higher frequency because of that. And it does depend upon the mass per unit length. The final thing, let's talk about the harmonic structure. Again, we're talking about objective and subjective. And the harmonic structure is what we have when we talk about what it sounds like in terms of overtones and so forth. I guess actually I should put that right here. Overtones. But this is our harmonics and the oscillations that we have And this describes exactly what this sound wave looks like. Whether I have this, and then another wave that does half as much, this would be called an overtone of this other wave. And these overtones and this harmonic structure leads us to a subjective quality of what we call the quality of the sound. The quality of the sound is what harmonic structure it is, what frequencies are all overlaid with one another. Not just one cosine, but many cosines. And that enables us to distinguish a flute from an oboe, from a human voice, from a piano, even when they're playing exactly the same note. It's the mixture of these harmonics or overtones. And we'll talk about that quite a bit more in the work that we have coming up.